Note that this video is meant for someone with mathematical knowledge up to an Algebra 1 level, so a lot of simplified concepts, especially logarithms, will be used. I've tried to make the steps as short as possible without touching all the parts in calculus, but anyways, enjoy the video. Last time, we looked at the definition of a derivative using limits, the thought process behind it, derivatives for polynomials and x to the n type functions, a bit of antiderivatives, and finally with a question of finding the function with the derivative of 1 over x. I highly recommend you see the full process if you're not familiar with the set concepts in calculus. So continuing on, what kind of function would have the derivative 1 over x? Well, enter logarithms. Using information about exponents and exponential functions along with inverse functions, we can define logarithms. A logarithm of base nx is the inverse function of n to the x. From this, we can derive some useful properties. For example, log base n a plus log base n b equals log base n a times b. This is like the opposite of what happens in the exponential realm, where n to the a times n to the b equals n to the a plus b. Similarly, since dividing the outputs is the same as subtracting the inputs in exponents, subtracting the outputs is the same as dividing the inputs in logarithms. Anyways, you might be wondering, what the heck do inverse exponents have with 1 over x and derivatives? Well, a long time ago, some guy figured out that the antiderivative of 1 over x looks awfully a lot like a logarithm. So a special logarithm of base n, let's say called ln x, meaning natural logarithm, was made. This function will be defined by the fact that its derivative is 1 over x. So let's plug in ln x into the limit definition of derivatives and figure out the base. We get limit h goes to 0 ln x plus h minus ln x over h. We can use the neat property of subtraction in logarithms to get ln 1 plus h over x in the numerator. You might be alarmed for a moment since you're dividing by x, which could be 0. But the thing is, we can't put 0 into a logarithm anyways. Consider this: if the input for the logarithm is 0, that means that for the output, if we put it back into an exponential function, the second output would be 0, since the two functions are inverses of each other. However, there's no real value, which results in 0 in an exponential function, or in other words, there's no output for x equals 0 in a logarithm for real inputs. Alright, so continuing on, we get limit h goes to 0 ln 1 plus h over x over h. Now we use another property of logarithms. Multiplying something to the output is the same as raising the input by a power. You can confirm this again with exponents. Multiplying something to the input is the same thing as raising the output to a power. Since x is a changing value, we multiply 1 over x over 1 over x, then let the magic happen. Alright, so we have a relatively simple limit h goes to 0 1 over x times ln 1 plus h over x to the h over x. Since x is a constant, we can pull out 1 over x, but we still have to worry about the latter part. One might be tempted to just plug in h equals 0 to the expression, resulting in ln 1 to the infinity. 1 to any number is just 1 anyway, so that leads to ln 1. Wait, but ln 1 is actually 0. If the limit is 0, then the whole derivative becomes 1 over x times 0, or just 0. Clearly, that's not the derivative we were looking for. Well, then, is there just really no function having this derivative? As it turns out, we made a mistake. The limit of ln 1 plus h over x to the h over x is not 0, but instead a special number. E, or Euler's number, is defined as limit n goes to 0 1 plus n to the 1 over n power. You might think that this is just 1 to the infinity power and becomes 1, but as you get tinier and tinier values for n, which are closer and closer to 0, it actually goes to a separate value, e. In the derivative formula we have right there, we see the limit definition of e, albeit with h over x instead of n. However, x is a constant, so it doesn't matter in this case. H over x going to 0 is just as good as n going to 0. If you're still a bit unclear about this, think about the limit this way. Since both n's in the first limit goes to 0 at the exact same rate, in both instances of h over x in the other limit goes to 0 at the exact same rate again. Even if it's not the same rate as the first limit, both are essentially the same. Moving on, since you want the final product to be 1 over x, the logarithm must become 1. Since we know that the inside part goes to e, the base of the logarithm must also be e. Note that log base AA is just 1, since a to the first power is a. Using these, we can finally find that the mystery logarithm has a base of e. So we've solved it. ln x with base e is the function which has a derivative of 1 over x. Maybe e is just some random scary irrational number, one might think, but it's practically a main character in calculus. If you put the base of an exponent as e, for example, we get some very crazy things going on. But the topics of today's video is about a glimpse of calculus and a specialty of ln x. It just stands out from all the other antiderivatives of x to the n form functions. Like, what's an inverse exponent doing in there? Anyways, I hope you liked the video.